Okay. All right. I think everything is good. Monday, May 25th. Good to see all of you. Some of you came to the question and answer on Friday, and I'm glad the people who came because it was really just a small sort of a Q&A session. And if you have any questions about any of the content, I think that's a great time to just ask those questions sometimes when I do live streams or even on Teams. It's hard to ask questions when it's like entire class, right? So imagine if we were in class, then if we were in class, we would just kind of, I'll come like right next to you and help you out. That's what the Q&A session was supposed to be. That was the intent. So if you have any questions, really, it's important for you guys to come in and ask. One thing about chemistry is that a lot of times we get sort of stuck on getting the right answer. I know you've heard of this already, or just like grabbing the numbers and put it into equation. And I think that's one habit a lot of people have, right? Because a lot of your questions are like that, where you just kind of grab the question at those numbers in the question, and then you immediately substitute into your formula, or just like, oh, I'm gonna do this and then put it into moles. That sometimes will not work because some of the wording in questions might be a little bit tricky. And as you will see in this unit that we're going to encounter, visualizing what you see, what the scenario is, really matter. Okay, so even when you guys do mole conversions or limiting reactants or stoichiometry or whatnot, make sure that you guys have sort of that grasp of what's happening, right? What are you making? What are you synthesizing? Instead of just like seeing the question and say, oh, first thing I'm going to do is just going to grab this number and change it into moles, or put it this or whatever. Try to visualize what the question is asking for first, and if it helps, just draw a picture of like, okay, here's a beaker of this content reacting with this content, and then once you have calculated the answer, then go and then see if it makes sense. I think that's a really important practice to have, is that did you calculate, like what did you calculate, and did the number you calculated make sense to what you did? That's one downside of doing this remotely, because we don't have any practical work. I can't just like tell you to make something and go to the lab and grab the ingredients to do so, the chemicals to do so, right? And I think having that sort of practical work will help you sort of understand that a little bit better. But because this is all like online and you just do worksheets, yeah, it's easy to sort of just, be used to just grabbing numbers and putting into the formula. So one encouragement I would say is that when you guys are doing the question, try to visualize what you're doing, especially this unit, because some of the wording could be tricky, and it could get you the right answer, and it could get you the answer that was supposed to trick you with, right? So that's one thing. I don't know how you guys have been doing and have heard the news that starting June 1st, like this is not confirmed yet, so nothing this is confirmed, but the government has proposed the reopening of phase 2. So on June 1st, school was part of that, but that means that it might be a smaller gathering. So it's not like, hey, we're all going to resume school again on June 1st, but more like we could have like a smaller one-on-one sessions or small group settings. We don't know what that looks like yet, but yeah, it's just gotten everybody sort of a little bit stressed out and anxiety inducing, because who's going to look after my kids? That's the thing. But that's yeah, I guess we'll have more information about that this week and see what that looks like. Hopefully you guys all got a chance to go outside this weekend. I was looking at this app. There's this new app. I was looking at bubble tea and all that stuff. I'm sort of craving some good bubble tea right now. And I don't know if you guys have ever tried bubble tea, but like there's this app that is called Food Highway, and it's just for like Asian food restaurants and like bubble tea restaurants. So like basically you can see like you can go down this entire list of bubble tea restaurants that you can order, and it's a delivery service, so it's like a like Food Dash and all that stuff. I'm not advertising for this. I just got this, and I just found it really fascinating that there's a lot of these sort of dessert places. If you have never tried bubble tea, I would totally recommend trying some bubble tea out, and milk tea is always great. I like, if you like tea, it's great. I wouldn't recommend getting 100% sugar because it's too sweet for me, but maybe like 75%, 50% is great. So I don't know, I'm sort of craving that and other things today. You know, sometimes you just have to do things to just bring you that little joy in life, I guess, especially right now. So since we're talking about bubble tea, we're going to talk about this unit called solution, because bubble tea or whatever drink that you drink is a solution. What a great segue. I did not even intend on that, but that's actually a really good segue, because we're going to talk about solutions. So I'm going to show you this OneNote that I updated. So if you want to check this out on the screen, I'm going to see if I can make it a little bit bigger. I don't know how big it is on your screen, but yikes. This is the updated for Unit 4, and let me see if I can. Oh, I can't zoom in this section, but this is on OneNote. It's also found in your Teams in your class notebook, and I would say hi to you, Carbon Messy Lee, but I don't know who you are. Yes, Junior, fire. I don't know what's your favorite flavor for bubble tea. Mine's just like straight up milk tea. There's one that's really good from Gongcha, from like on Osborne, and it's like the foam with winter melon. If you have not tried it, if you don't know which one to try, the winter melon with the foam is excellent. So anyways, I feel like I'm gonna have to order one now for lunch. But here's your OneNote. Here's your class notebook. I have updated this, so your work booklet is still there. So you have your work booklet questions. So hopefully you guys have had a chance to do your limiting reactants. If you still have questions on that, ask me, and then we can seriously schedule like a one-on-one sort of meeting so that I can help you with the screen. It's just like for the Q&A. Sometimes it's hard for me to respond through like typing on Teams, because it's so much easier for me just to, hey, look at this, this is what you do, and that's it, right? Because if I type it out, then it's just hard to sort of explain something just through typing. Your solutions your solutions unit will start right here. So I'm just gonna circle the page right here. So this is your unit 4. I don't know what page it is because it got cut off. It's like 100 something. And then your unit 4 solutions is here. So we probably won't get the chance to cover everything of this because it is a big unit, and I think judging from the calendar, we have sort of 4 live stream classes left. Like, it's last week of May, and we basically have like 3 weeks of classes left till that week of like exams and whatnot, or review or whatnot. We're not having exams, but like usually that's the exam week, right? So I have broke down the most important items that you need. So it's all here. I also have tutorial videos, so I put that as the first one, so if you get lost of where to find it, it's there. There's like unit 4.1, 4.2. All these are all the important things that we'll talk about, and yeah, that's where you find it. And then I'll do the notes here, like what is a solution. There's some notes that I provided, unsaturated, which we'll talk about, and then all of this stuff. And if you need the notes, it's all here. Notes 1, it's right here. Notes 1, I'm just going to move it over. So this is what we'll sort of talk about today, like what exactly is a solution, how do we break it down. So this is just a theory part. There's nothing calculating here yet. And then notes 2 is the calculation part. This is looking at like what exactly are you doing when you're dissolving something, what types of solutions can you make. And then the last one is really the practical aspect of making a solution, is that how do you make a solution with the proper molarity, right? And sometimes when I tell you guys about like, oh, this is a 6 molar solution or it's a 0.1 solution, how do we make that? How do we calculate that? And that's what it is. Yes, Moron, we're in May and we're leaving May. And classes are ending pretty soon, Marwan. I like how you changed your name to back to your real name. That's pretty good, Marwan. Hey, Marwan, did you see how many subscribers I have today? Suddenly, I have surpassed the 900 mark. I have 907 subscribers. I don't know how. It's crazy. It's just like one day I had like, I think we're starting this, it was like 850. Now I have 907. I just need 93 more subscribers before I can start monetizing my videos. So that's the thing. All right, let's get started then. Here's notes one. Let's kind of go through this because this is all theory, so it's probably easier for me to just go through all the pictures and notes with you. Basically, I have not gone viral yet, Island. I'm still waiting for you guys to make it viral, you know? I'm still waiting for you guys to make this viral. I thought we were going to do that song and that could have made it viral, but nobody did the song. Nobody wanted to play music or sing or anything like that. And nobody did the lyrics, or actually Hallie did do some of the lyrics, but then now it's just like sitting there. And I was like, okay, I even deleted that video of me playing on the piano off my YouTube because I was like, all right, nobody's doing this. So I was a little sad, but then I guess that's it, you know. Anyways, I think if we were to do that music video, I think Miss McCorby would be so impressed because it's like music and chem and all that stuff. But anyways, I think like Virgin Radio would probably, you know, play it. Anyways, well, didn't you subscribe to this already, moron? So like, you don't make that much money on YouTube, but I should say that I think my top video on YouTube is like 180,000 viewers, so that was pretty impressive. But that's over like five years or so or more. But yeah, so when we talk about solutions, it's really about what kind of solutions we have. It's really just mixing things together, right? Like if I were to look at my bottle of water, it's just water, right? And nothing has mixed into it. But if you were to make like lemonade, tea or coffee, you're putting substances in there, right? And the substances that's in here will get mixed in, and then eventually you get that solution that cannot be separated. So that's one kind of solution. On the other hand, if you had bubble tea, you know that you have your the liquid part, and then you have those bubbles at the bottom, right? That solution is still a solution, but it's now a solution that can be separated because you can take out those bubbles out of the liquid, right? So that's another type of solution. So basically when we talk about solution, it's just anytime you're mixing things in to make one sort of mixture. So if I were to say, I don't know what I have here, but I thought I had a bunch of beakers here, but if I were to, you know, I don't even have, oh, here's a beaker of like a tiny beaker. I have some garbage in here or whatever, and this in here can be a mixture because it's like solid mixing into something, right? So that's a mixture in itself, but that's not a homogeneous mixture because it can be separated. So let's look at sort of the classification or separation of this. When we think about matter, so this is anything that sort of exists, anything that we can touch and feel or whatever, that's matter. And that can be branched off into like pure substances and mixtures. So when we think about pure substances, that's like the stuff you find on your periodic table. So if you go into your parents' jewelry or your mom's jewelry box and find a gold ring, gold is an element. That's a pure substance. That means that if you were to break it down, you know, hammer it or whatever, that material, that substance will not change into anything else. It'll just be gold atoms, right? That's a pure substance. And if you think about the next branch is compounds, just like same thing for like water, like H2O. If you were to break down the water, I know it breaks it down into your hydrogen and oxygen, but the properties of this liquid was still going to be water. If you take it, you know, make it super fine or filter it, it'd still be H2O. So that's still a pure substance. So that's a compound. Or if you were to think about like table salt, which is your NaCl, right? If you were to break it down, that's still going to be NaCl. It still share that same property. That's the key part. Keyword is that pure substances, they maintain those same properties, the physical and chemical properties. It's not going to change. When we look at the other side, mixtures, that's when you mix things in. So you have like homogeneous and heterogeneous. So this one is just like the bubbles, in bubble tea. You can separate it, or it's just like sand in water. Whereas homogeneous, you cannot separate it. So we're gonna we're gonna look into this a little bit more deeper. Can't separate. Let me just gonna finish writing this with a mouse. Can't separate. So if we were to look at the differences between the two, pure substances really are all the particles have the same properties. So they can be like hydrogen gas, right? Hydrogen gas is H2, and then sugar is just like sugar, right? Like if you were to take a cube and then grind it, that grinded up granules of sugar will still taste sweet. It still has the same properties of your cube, right? That's a pure substance. Whereas mixture is that you will have more than one kind of particle. So here is a diagram of this. So pure substance, you can still have two different elements, right? Just like sugar, salt, whatnot. The key part here again is that these one will have the same properties when they're still together. These are all, they will still have the same properties, right? Whereas in a mixture, their individual components will retain their properties. So like salt water, for example, you can have salt that you can take out, water you can sort of condense. So both of these will remain with their own individual properties. So like if this is your salt and this is your water, they will still retain their own property. That's your mixture. Or concrete is just a mixture of various different substances put together, right? Like different gravel or sand or whatnot, right? That's a mixture. Can somebody answer Marlon's question if we have an exam or a test? I feel like he's missed out a little bit here. I think you guys know. I think I answered that question last week, so you guys can totally answer that question. So homogeneous, the types of mixture here. So we're looking at mixture. Homogeneous means really evenly distributed. So when salt and sugar are dissolved into water, the salt or water spreads out evenly and it's not easily separated. Whereas heterogeneous one is not evenly distributed, and it's like sand or water. Sand and water or salt and pepper, like you can separate that, right? That's a big difference. You guys don't know the answer to that, like the exam? Have you guys like you guys should know this. I talked about this last week. Tell me what you guys think. Should we have exam for this? And then for different kinds of mixtures, that can be a little bit more gray area. It's not like clear cut, like I can separate the sand from water. So you can have like suspension mixture and emulsion mixtures. You guys are so funny. So concerned about this exam. I'm just going to let you guys sweat it out a little bit. So when large component solids are found in solution, they're called a suspension, just like your big bubble tea. And emulsions, this is where you have like two liquids. So mayonnaise is one of them, and you can actually, if you leave mayo out, you can eventually separate, right? You can have two different ones. Why did you retract? There you go. Thank you, Junior. We do not have exams. We don't have. Why did you retract your message? We don't have exams. I think I talked about this last week and saying that we don't have exams. I'll get you guys to continue doing those like assignments and quizzes on your teams. You will probably do a self-assessment, a thorough self-assessment next week, and you're gonna tell me what you have understood and learned and how well you fared with this. And yeah, it's great that you don't have exams. Remember, you have grade 12 chem next year, so learn for the sake of learning. Understand the content. Right? That's what your focus is. Don't focus on like I need to, I don't know, do a test or just like learn like what this is about. Like I try to like this stuff or not love this stuff. It's interesting. Anyways, homogeneous mixtures are where you have are known as your solutions. Like they're that sort of the properties will stay the same. So even if you were to leave out like salt water, they will be evenly distributed. That's your solution, right? Your homogeneous solution. And you can't really filter salt water or like sugar water, right? That's your homogeneous solution. So that's what like a solution is. The colloids are like gels. So if you have gels, they're not homogeneous mixture, even though they seem to have similar properties. That's what I was trying to say. But like that's your mixture. That's your theory. So when we define something that's a solution, right? Like if we were to have a drink like of tea here, right? A homogeneous mixture is just where they're evenly distributed. So when you put like sugar and water in here and you stir it up, or just like your Kool-Aid, this solution is going to look the same at the top to the bottom, right? That's your homogeneous solution. It's well mixed together and it will not separate. But then how do we determine like sort of like the names for what gets dissolved in? Right, so here's I know I'm going through this theory really fast, but like let's see if you guys can follow along here. Here's your Kool-Aid. Here's your Here's your cup, and then to make Kool-Aid, you're gonna put some water. So you're gonna put water in here, and then you're gonna put a pack of let me change colors. Sprinkle a bunch of Kool-Aid powder in here, right? Since you're making a solution, there are sort of names to classify this, right? This is, oh man, this is off the screen. This is your Kool-Aid, right here, Kool-Aid powder. So this is, so what's the name to sort of identify these two things in a solution? Well, there are two names, solute and a solvent. Those are two big things that you guys have to know. Very simple in a way that solute somewhat sounds like solid. So the solute is the one that's dissolving in the solvent. Okay, so the solute you put in is dissolving the solvent. So one way to remember this is solute sounds like a solid. So that most of the time, I'm going to say most of the time, that your solid, like your sprinkled sugar granules, your Kool-Aid powder, most of the time that is your solute. And then the stuff you're dissolving into, like your liquid stuff, like your water or whatnot, that's your solvent. Okay, so that's your difference between a solute and a solvent. However, what if you were to mix two liquids here, right? What happens when you're mixing bunch of these hand sanitizers that we use, right? So this is isopropyl alcohol, and this is 95% alcohol, incredibly strong, right? So how do we define which one is your solute and which one's your solvent? So one big thing is that it's really easy, is that solvent is the one with the higher percentage, or the dominant one. Okay, so this is your dominant one. So this one, because your alcohol has the bigger amount, that's your solvent. And now this water is actually dissolving into the alcohol. You're putting water into the alcohol, so that water is your solute. So don't always think solute is always a solid, because you can have liquid solutions. Just remember that the solvent one is the dominant one. Is that good? Like we will forever remember that, right? That's good. Then let's move on. I'm gonna bypass the types of solutions. I'll let you guys read this, but these are just the different possibilities, combinations of solutions. Like you can mix solid into a liquid, right? Like sugar. You can mix liquid into a liquid. This is just like drinking alcohol. You can mix gas into liquid, just like your carbonated water, right? Or you can have solid in a solid, which is like brass, because brass is your copper and zinc. You guys play brass instruments. That's how they make that, copper and zinc. You can have liquid into a solid. This is like your dental amalgams. If you ever have any like filling or covering for your teeth. Gas into your solids. This is like gas and carbon filters. So if you have filters, there's some gas particles that's trapped. Also, you can have like solid into a gas, where again, gas is the dominant one. This is your solvent. So just like dissolving microparticles in the air, just like coronavirus in the air, right? Those viruses in the air, that's your solute. The air is your solvent. And then liquid in gas gas, like this is like your water moisture, and then gas and gas is just like air, because air is a mixture of various gases, right? So that's your different sort of possibilities or combinations of solutions. That's it. All right. One thing I wanted to also talk about is I think it's important because this is water, and water is what we call the universal solvent, right? Because anytime you spill anything or make anything, you always put the solvent into water. Why water? What makes water so unique in dissolving things? If you really want to extrapolate this and think about this, like in this grand scheme of life, water is so important, and really it breaks it down into this water having this bond angle. So you all know that water is H2O, but it has this angle that makes it unique, and also the properties of hydrogen and oxygen. So what this is that now we're getting into a little bit more of a theory to classify what kind of bonding occurs, right? So here's the structure of water, and what it is that if you this bond between this hydrogen and oxygen is what they call a polar bond. And what a polar bond is, that you have to think about these now in that very chemistry way, is that your elements have protons and neutrons and electrons. Only the electrons are found on the outside of your atom, right? So we're just going to think about electrons here. In what a polar bond is that now when this hydrogen and oxygen are bonded, right? Like you know that H has a +1 charge and O has a -2. That's why you need two of these H's to bond with one oxygen, right? That's the combination. So when you're looking at this is all about sort of balancing that electron. And a polar bond basically is that because oxygen has this ability to grab the electrons itself, because it has that very high, what they call the high electronegativity. So the electronegativity. Oxygen has a high electronegativity. That means it's going to grab the electron to itself. So the electrons are going to hover around this oxygen. So I'm going to see if I can show you this picture here. Oh, excuse me. Good night. Go for your nap. So here, if we were to visualize this, right, oxygen is going to have a lot more electrons around the oxygen compared to the hydrogen, because oxygen is going to grab those electrons, attract those electrons from hydrogen. So it's going to make this oxygen have this partial negative charge. This is important because this partial negative charge will help dissolve things. Well, since oxygen grabbed those negatives away from hydrogen, then it's going to leave hydrogen with this positive charge or partial positive charge. So in a nutshell, I'm just going to redraw this. Hydrogen or water, it's going to look like this. It's going to have, this is delta, and this is what they call the electronegative value. So this is going to have that partial negative charge. That's what you have to remember. And then hydrogen and the hydrogen atoms will have this partial positive charge. It is because of this reason that allows water to break down a lot of substances and dissolve things. It's because of this polar bond. Okay, so if you look at this, other polar molecules exist as well. It's not just water, but like ammonia, sulfur dioxide, hydrogen sulfide, all of this stuff are polar molecules as well. That means that their electrons are not evenly distributed. Okay, so if we were to look at this picture, you're going to see this in grade 12 again, but oxygen, why it's bigger is because there's a lot more electrons surrounding it, and also it's a bigger element, but hydrogen has this, leaving it with positive. So because of this sort of polarity, that's why it's called polar bond, polarity, there's a difference of charges. It makes it a lot easier to dissolve things. I'm going to take a 5-second break. Let me know if you have any questions about that, what a polar bond is. All right? Is that okay? Are the people in the last slide bound to water? Yes, you're correct. They are bound to water because the water is really important. And water, if you remember, when it freezes, it floats. If water didn't freeze, if it didn't float, there wouldn't be all these ice caps, right? Pretty interesting to think about the importance of water, how that is. So this is the definition for electronegativity. It's the tendency for electrons to pull the electrons itself. We'll talk about this a little bit more thorough next year in grade 12. But basically, I just want you guys to have the introduction of what this is. Basically, electronegativity is how selfish an element is in grabbing electrons to itself. That's all it is. Okay? So when we look at the different bond types, there's two different kinds. There's something called nonpolar and polar bond, which we have talked about. So polar bond, that's where the electrons are not evenly shared. So it's like you and your siblings, you get more toys than your siblings. That's a polar bond. That's like a sort of a uneven distribution, right? Not fair. Whereas a non-polar bond, that means non-polarized, right? If it's not polarized, that means it's even. So this is like even. Everybody gets the same sharing, right? If we hold hands, everybody's tugging at the same strength. That's a non-polar bond. The key thing about that is that polar bonds and non-polar bonds, or non-polar bonds and polar bonds, they don't mix. So when we think about oil and water, the reason why they don't mix together is because what kind of bond is water? Polar. And because oil is like a fat, this is non-polar. That's a reason why they don't mix, because one is polar and one is non-polar. Very interesting. And this is to determine if a bond is polar or not. So this is a table. We won't talk about this this year. We'll leave this for next year. We'll go into more details of that for next year. Okay. And then the rules for mixing solutions. Again, this is the picture, right? How come some liquids can mix with some and not others? So this is water and alcohol, right? This is really just ethanol and H2O. They mix into a nice homogeneous solution. This is oil and water. You can see that there's a clear separation. So the question is why, right? So the rules behind that is that only if you're polar and if you're polar, you can mix. If you're non-polar and non-polar, you can mix. But if you're polar and non-polar, they will not mix. Okay? So since alcohol is polar, water is polar, that's why you can mix and have alcohol beverages, right? On the other hand, water is polar, oil is non-polar, they won't form a solution. So I hope you like my hand gestures. That's really it for the first about the theory of solutions. What I would say is that here's that example, this demo that I showed you. I'm gonna again pause it, let you guys ask me any question here. Do you guys have any questions about this? Remember we did this ammonia fountain, right? Remember this? You have this inverted sort of round bottom flask. This is stoppered. It has this glass tubing. It sits on top of this water, right? And there's like a little bulb or syringe with water in there. Inside here is ammonia gas, which is polar. And then remember how we initiated this reaction is that once we squirted this water into here, right? And then all this water is going to rush up this tubing, and then it's going to create this fountain effect to spray the water in there, right? So we did this, the first unit is like, or in the second unit, it's like, why, how does this happen? Do you guys remember how to explain something like this? A key part here is now looking at the polarity of this, right? Ammonia gas is polar, water is also polar. So why would that matter? Give it some thought. If you were to squirt this water into here, what's going to happen to the ammonia gas? Well, since ammonia gas is polar, water is polar, the ammonia gas is going to dissolve into the water, I should say. And because ammonia gas dissolve into the water, what's the pressure, or how much space do you have left? Well, instead of all the gases pushing against it all along, now your gases all sort of settle into that water, which is finite volume, and then you don't have as much space. That means the pressure inside drops, and you have atmospheric pressure on the outside, so you have that pressure difference. Atmospheric pressure pushes the water up, and that's how this works, right? This only happens because of the polarity between the ammonia gas and water. Does that make sense? You guys remember that, right? That's your ammonia fountain. And lastly, your gases in the air are also nonpolar. So they're also nonpolar as well, and that's why they mix into that as well. So one really unique thing is that, remember last week we did the Mentos experiment, right? Here's your Coke bottle, and when you put the Mentos candy in, it disrupts all those CO2 gases, those little bubbles. And because in the Mentos candy there's a lot of grooves, those nucleation sites, right? Like you guys all talked about this in your assignment. These tiny microscopic nucleation sites actually disrupt the gas bubbles, those carbon dioxide. So as your Mentos falls down, it disrupts more and more, and as more carbon dioxide gets disrupted, it causes this exponential chain reaction, right? So then that's why it erupts like a geyser. So how come carbon dioxide will have to come out of the solution? Well, look at the type of bonding in this. Carbon dioxide is a non-polar molecule. What about water, right? This is all dissolved into water, right? Water, again, is polar. So naturally, carbon dioxide actually doesn't form a good mixture with water. So that's why all of those drinks that you drink, like Coke, Pepsi, Fanta on the list, those carbonated drinks, they're pressurized. That means that carbon dioxide has to be put into that with pressure, force it in there, and then has to be airtight. So then that carbon dioxide will be contained, right? But once you open it, you hear that fizz. That means carbon dioxide are readily just going to naturally escape, right? Because it doesn't dissolve into water naturally. So if you leave Coke out, it goes flat, because eventually that carbon dioxide, because it's nonpolar, will come out of the solution. Does that make sense? Does that make sense of why like drinks are carbonated, right? And if you think about that and extrapolate that message, is that, or that idea, well, think about like our oceans and all of that as well, right? So some of the gases will not go into the water because it doesn't dissolve that naturally, right? So it does require some of the atmospheric pressure to sort of allow that molecule to sit on there, right? Or to dissolve into the water. So that's gases in a gas or into a liquid. How is that so far? Is that okay for everybody? For this theory, I know I talked a lot about the theory. I'm going to talk about this next time. I don't want to rush too much into this because I think I just gave you a lot of theory right now. So I just want to stop it there. Are there any questions about this? So today we learned about just basically what a solution is and different types of solution, and then and how we dissolve things such as like polar and non-polar. On Wednesday, I'm going to talk about the chemistry behind like what happens visually. What do we see when you dissolve like sugar or dissolve salt? Because then that's when we start to write your chemical reactions with that. And then that's called the solvation process. That's over here. Here on the screen right here. And then we'll talk about 3 different kinds of saturated, unsaturated, etc. So I'm going to show you one sort of preview about what that means before we end it off here. And if you look on the screen, which screen am I looking at? That's the better question. hold on a second. This one, no, I want that. I don't want this. There we go. So this is supersaturated. We haven't talked about supersaturated solution yet, but this is pretty cool. This is what we usually do in class. This is calcium acetate. So initially you start off as a liquid, a transparent liquid, but as you pour it out, it turns into a solid, right? Super cool. And this is a supersaturated solution, and we'll talk about what that means, right? And here's another supersaturated solution.
Good grammar and spelling are important, but if you want to write essays that inspire...
There you go. So this is a supersaturated solution.
Is
It's a clear solution.
almost 3 years old, and it's been used over and over again.
And
Acetate. And pull the stopper out and shake them in.
once he
And you
puts
can see
some powder
almost
in,
instantly
some of the crystal
all those
in,
other
it
sodium
crystallizes
acetate
out
Ions that were in there are now getting together and
and
solidifying.
turns in solid. So
They
where else
found the
have you
crystal
seen something like
structure.
this, right?
And
So that's your supersaturated solution, which we'll talk about. Let me see. Whoop, where is my screen here? Nope, not that one. Whoop. I have lost my screen. Give me a second. Oh, I totally lost it. I don't know what happened here. My face is gone from this. Anyway, so that's your... I'm trying to figure this out. There we go. So that's your supersaturated solution, which we'll look at next class. Please let me know if you have any questions. And yeah. All right. If you have any questions from before, please ask me as well. If you haven't had the chance to do that quiz or assignment, please do that. I want to know how you guys are doing with this, right? I know it's remote learning, and I can't be there to like watch you guys do this, but please do make the attempt in doing those questions and submit it to me, please. Okay, that's it. I'll see you on Wednesday. Go get some bubble tea. Okay, bye. I don't know where my mouse is.